Hello Calc 3 and welcome back to another video. In this video we'll be covering section 15.4 on double integrals in polar form. So remember back to the beginning of the class when we reviewed chapter 11 that we reviewed the notion of polar coordinates, functions in polar coordinates, and then ultimately how to take integrals of functions that are given in terms of polar coordinates. And it just so happens that we can also take double integrals of functions using polar coordinates. And that will be the goal for this video, to build up the notion of a double integral for functions given in polar coordinates. So let's get to it. So let's let f of r theta be some general function in two variables where the points are given in polar coordinates, hence why we use the variables r and theta. And we can let r be some region in the plane. So I have a diagram that I conveniently took from the book. The region R is the region in blue inside of the diagram here. And remember that for the double integral in rectangular coordinates, we subdivided the region R into a bunch of smaller rectangles, which we ended up calling a partition of R. Well, here we're going to subdivide using what we call polar rectangles, which is kind of like the polar analog of Cartesian rectangles. And each of those polar rectangles is represented by a change in theta and a change in r, which we call delta theta and delta r. So you can look up to the polar rectangle that they have highlighted in red in the diagram, and you can see that we can kind of think of the width, if you will, of the polar rectangle as delta theta, and the height of the rectangle, again, if you will, not exactly, as delta r here. And also notice that we can describe this region R in terms of polar coordinates as opposed to rectangular coordinates. So we say that R is the region where theta is bound between alpha and beta. So in the diagram, that's given as these two rays here. So we know that theta has to be between those two rays. And we also have bounds for R, or the distance away from the origin. So we have two functions that are given in terms of theta. We have r equals g sub 2 of theta and r equals g sub 1 of theta. And our region is going to be, or all of the r inside of the region are going to be bound between those two functions. So r is going to be between g1 of theta and g2 of theta. And this is a way to describe the region r using polar coordinates as opposed to Cartesian coordinates. And the collection of all of the polar rectangles that are contained completely in R, so this is what we said in section 15.2 as well, they have to be contained completely in R. That's going to be a partition of R, where the partition consists of these polar rectangles. And just like before, the double integral is going to be defined as, and here we have the double integral of f of r theta over the region R is equal to the limit as the norm of that partition goes to 0 of the sum from k equals 1 to n of f of r sub k theta sub k times delta a sub k. So here, this is the area of that polar rectangle. This r sub k theta sub k is a point that we choose for each of the polar rectangles inside of the partition. So this is very similar to the definition that we had before. It's analogous, we're just using polar coordinates this time instead of Cartesian coordinates. But the only problem we have left to solve here is that we need to find an expression for the area of the kth polar rectangle using delta theta and delta r. So in the case of rectangular coordinates, this ended up just being delta x times delta y, because the area of a rectangle is equal to width times height. But the problem here is that the area of these polar rectangles is a little bit tougher to come by. So our goal here is to figure out how we can write the area in terms of delta theta and delta r. So for convenience, we're going to let each of the r sub k's that's showing up here, we're going to let each of those r sub k's be exactly in between the r values that form the polar rectangle. So remember that when we do these, when we take these Riemann sums, we can choose a point anywhere inside of this polar rectangle. So I could choose that green point that I just drew up there as well. But for convenience, the formulas actually look nicer when we're trying to solve for area here if we just assume that we're choosing the point directly in the middle. So let's just say we're choosing the point in the middle here. Okay, then the inner radius of our specific polar rectangle is going to be equal to r sub k minus delta r divided by 2. And the outer radius for our specific polar rectangle is going to be equal to r sub k plus delta r over 2. And this is just using the fact that r sub k we've now assumed to be in the middle of our polar rectangle here. And if that's a little bit confusing, I would just pause the video for a second and think about why that is the case. I don't think it's too tough to conceptualize, but maybe it'll take a little bit of time. Okay, and then the area of the polar rectangle is going to be given by this expression down here, which looks pretty nasty at first, but this expression is coming from the formula for the area of a circular sector, which I have given over here. So if you have an angle theta, and this angle, you can think of it as being part of a larger circle. So let's say I have a larger circle in green that's going around like this, and I want to know what the area of that sector in blue is. Well, that area is going to be equal to 1/2 times theta times the radius of the circle squared. So this is just a formula from geometry that now we're going to be using. So the area of our specific polar rectangle is going to be equal to 1/2 times delta theta times r sub k plus delta r over 2 squared. So notice that this is the outer radius squared, minus 1/2 times delta theta times r sub k minus delta r over 2 squared. So this is the inner radius squared now that we just found out. And this is going to, so geometrically what's going on here, you can think about our polar rectangle being this thing in red right here. So what we're doing is we're taking the area of the whole sector in blue minus the area of just the sector inside, like that. And what are we left with? We're left with just the area of the polar rectangle in red. And then we can do a little bit of algebra with it, and it ends up being the case that the area of the kth rectangle is equal to r sub k times delta theta times delta r. Okay, so now we can use this information and substitute it back into the definition that we had above. So the double integral of f of r theta over the region R is equal to the limit as the norm of the partition goes to 0 of the sum from k equals 1 to n of f of r sub k theta sub k, and here is the distinguishing factor now for taking double integrals with polar coordinates. We have this r sub k that is left over here because of the area formula. So remember, for Cartesian coordinates, we had that the area was just equal to delta x times delta y. So there was no extra variable that came out in front of that. But now we have this extra r sub k that's coming out in front of the expression for the area, and that carries into the Riemann sum. And so we can write this as the double integral of f of r theta times r. So now we have this extra r, dr d theta, over the region R. So the double integral of f of r theta over the region R is equal to the double integral of f of r theta times r dr d theta. Okay, so this is a way to now represent the double integral as an iterated integral for polar coordinates. And so I list that down below here in this blue box. This is kind of the important formula, the most important formula I think of the whole video here. So the double integral of f of r theta over the region R is equal to the following iterated integral. So we have the integral from theta equals alpha to theta equals beta, so those are the bounds for theta, of the integral from r equals g sub 1 of theta to r equals g sub 2 of theta, so there are our bounds for r, of f of r theta times r dr d theta. So again, the real novelty here is that we have that extra r that we have to remember to add in when we're taking the double integral. All right, now we can move into our first example. So let's say we want to find the limits of integration for integrating a function in polar coordinates f of r theta over the region R that lies inside of r equals 1 plus cosine theta and outside r equals 1. So r equals 1 plus cosine theta is a cardioid, r equals 1 is just a circle. And one of the questions that I ask on quiz 5, I think uses this same region here, but you actually have to evaluate in that case. So in this case, we're just finding the limits of integration. So the first thing to do, like always, is to sketch the region. So I have a diagram that I've given on the left here. We have our plane, and then we have our cardioid, r equals 1 plus cosine theta, that's given in purple, and we have our circle given in green, r equals 1. If you're wondering how I know that 1 plus cosine theta looks like what I've drawn there, well, honestly, either just experience because I've seen it before, or you can start plotting points and you kind of get that shape to pop out, or if you really wanted to, you could just plug it into some kind of graphing program online, and that would be fine. I don't mind that at all, especially not for polar coordinates. So r is bounded above by our function r equals 1 plus cosine theta, and below by r equals 1. So you can think about that as if we start at the origin and we start drawing rays out from here, notice that the ray is always passing through r equals 1 first and then exiting through r equals 1 plus cosine theta. So that tells us that r is bounded below by 1 and bounded above by 1 plus cosine theta. We also know that theta is between negative pi over 2 and pi over 2 because the region goes from down here to up here. So the area is going to equal the iterated integral, where our first integral is the integral from negative pi over 2 to pi over 2 of the integral from 1 to 1 plus cosine theta of f of r theta times r. Remember, we have to add that in there, dr d theta. Okay, and just like we went from the definition of the double integral on 15.2 for rectangular coordinates to talking about area using rectangular coordinates and double integrals, we now have an expression for area of functions given in polar coordinates. So if R is a closed bounded region in the polar coordinate plane, so the plane where we're talking about R and theta, then the area of that region, A, is equal to the double integral of R dr d theta over the region R. So again, the novelty here is that we have to remember to add that R in when we're taking integrals with respect to polar coordinates. Okay, so let's move on to the next example. In this example, we want to find the area that's enclosed by the polar curve r squared is equal to 4 times cosine of 2 theta. And again, the first step for these kind of problems is to sketch the region. So we know exactly what we're talking about when we're trying to find limits of integration. So I've provided a sketch there. It's the region that kind of looks like a bow tie. So again, you might be asking, well, how do I know that that's what the region is going to look like? Just plotting r squared is equal to 4 times cosine of 2 theta might be kind of difficult. And again, I think my answer would be the same as it was before, where either you're going to know what this thing looks like by experience, you can try and plot some points, get some information about it or something like that, and then give a good approximation of what it looks like, or you can just use some computer software. Any of those options would be fine. There's no like cut and dry answer for how to figure out what these regions are going to look like. But we should notice that there is some symmetry here with our region. We have symmetry across the x-axis, and we also have symmetry across the y-axis. And we can use that symmetry to make our integration a little bit easier here. So if we can find the area of just the portion of the region in the first quadrant, then we can multiply that area by 4, and that'll give us the area of the entire region inside of the bow tie here. So we can write that the area is equal to 4 times the following iterated integral. We have the integral from 0 to pi over 4 because theta is bound by 0. So this ray that's right here, and this ray right here, which is at theta equals pi over 4, of the integral from 0 to 2 times the square root of cosine of 2 theta. So again, r is going to be bounded below by 0 because it's going to go all the way back to the origin, and it's going to be bounded out or bounded above by that curve r squared is equal to 4 times cosine of 2 theta, but we can just take the square root of both sides there and get that r is equal to plus or minus the square root of 4 times cosine of 2 theta. But because we're working in the first quadrant, we're only worried about the positive half there. So we're worried about positive the square root of 4 times cosine of 2 theta, which is just 2 times the square root of cosine 2 theta. And then again, because of the theorem that we had above, it's the integral of r dr d theta. And now we're just going to evaluate these integrals, do some calculus, do some algebra. So we worry about the inner integral first. Notice that the integral of r with respect to r, or the antiderivative of r with respect to r, is going to be 1/2 times r squared. And then we evaluate that from 0 to 2 times the square root of cosine 2 theta. So notice something really interesting here. In section 11.5, we talked about how when you wanted to find area that was enclosed by a polar curve or area between polar curves, we would always take the integral of 1/2 times r squared. And now we can kind of see why that's the case. So this is a nice way to build up why it is that even when we're doing single integrals and we want to find area bounded by polar curves, we use this 1/2 times r squared. Because if you think about it as double integrals, we're taking the antiderivative of r with respect to r, which gives us that 1/2 times r squared term. So that's kind of interesting. Anyways, so we plug in 2 times the square root of cosine 2 theta for r, and we get this 4 times cosine of 2 theta here. And if we would plug in 0, we would just get 0, so we're not going to worry about it. We can do a little bit of simplifying, and we get down to this 8 times the integral from 0 to pi over 4 of cosine of 2 theta d theta. Well, the antiderivative of cosine of 2 theta is going to be 1/2 times sine of 2 theta, which is why that 8 went from an 8 to a 4. And we evaluate at pi over 4 and 0, and we end up finding that the answer is equal to 4. All right, now for the last relatively big topic for this section here, we're going to talk about converting from functions given in Cartesian coordinates to functions in polar coordinates. So we're going to take double integrals that are defined in terms of Cartesian coordinates and rewrite them as double integrals in polar coordinates. And the conversion ends up being what you would expect most likely. So let's let f of xy be some function in 2 variables given in Cartesian coordinates, and let r be some region in the plane. Then we can convert f of xy to polar coordinates, or a function in polar coordinates, by using the substitutions x is equal to r times cosine theta and y is equal to r times sine theta. So again, those are things that we covered at the very beginning of the class in chapter 11. And then we can describe the region R in terms of polar coordinates instead of Cartesian coordinates. And once we've done that, then we can write the double integral of f of xy over the region R is equal to the double integral of f of r times cosine theta, r times sine theta. So here we've taken x and replaced it with r cosine theta. We've taken y and replaced it with r sine theta. We have to remember to multiply this r here because we're going to replace dx dy by r dr d theta. We have to remember that r. And again, we're taking the integral over the region r, but r is going to be defined in terms of polar coordinates as opposed to Cartesian coordinates here. That will give us our limits of integration. Okay, and again, let's move into an example where we use this fact. So let's say we want to evaluate the double integral of e to the x squared plus y squared over r. Well, notice right away that taking the integral of e to the x squared plus y squared with respect to either y or x is going to be very difficult and basically impossible with the methodology that we have. So being able to rewrite that function in polar coordinates is actually very important for being able to calculate this double integral. And anyways, R is going to be the region bounded by the x-axis and the curve y equals the square root of 1 minus x squared. Okay, so again, we're going to sketch the region. That's always a good place to start. We know what the x-axis is, of course, and then we have the curve y equals the square root of 1 minus x squared. Well, that's just the positive half of the circle of radius 1, or the unit circle, or the unit disk. So again, it would be very difficult to integrate in Cartesian coordinates. We actually can't represent the integral of e to the x squared plus y squared using elementary functions. So instead, we're going to describe the region R in polar coordinates, and then we're going to convert the function e to the x squared plus y squared into a function using polar coordinates. So let's start off by describing R in terms of polar coordinates. Well, again, we're talking about a unit disk here. So this actually converts over to polar coordinates really nicely. I mean, better than it does in rectangular coordinates. So R is going to be between 0 and 1, and theta is going to be between 0 and pi, because we're only talking about the top half of the unit circle here. Okay, and then the double integral of e to the x squared plus y squared dy dx over R is equal to the iterated integral, where we have the integral from 0 to pi of the integral from 0 to 1, and here's our substitution, where we're turning this function into a function of polar coordinates. So remember that x squared plus y squared is equal to r squared. We talked about that in chapter 11 as well, so that's why we have an e to the r squared now. And then again, we have to remember to multiply by this r here. And then, of course, we have dr d theta. Okay, so we take the antiderivative of e to the r squared times r. That ends up just being 1/2 times e to the r squared, and we're evaluating from 0 to 1. So we plug in a 1, and we get a 1/2 times e. We plug in a 0, and we get a 1/2, because e to the 0 is going to be 1. So ultimately, we end up with the integral from 0 to pi of 1/2 times e minus 1/2 d theta. And taking the antiderivative of these constants shouldn't be too difficult. So we end up with 1/2 times e minus 1 times theta, evaluated from 0 to pi. We plug in the pi, and we get a pi over 2 times e minus 1. So that would be the area of, or I should say, that would be the value of the double integral over r of e to the x squared plus y squared. Okay, for our next example, we want to find the volume of the solid that's bounded above by z equals 9 minus x squared minus y squared, and below by the unit circle in the xy plane. So again, a good course of action, what we're always going to do is just sketch the region that we're talking about in the plane here. So it's given as the unit circle in the xy plane, so I've drawn that in green. And in this case, it ends up being much easier to give our region in polar coordinates as opposed to Cartesian coordinates. So we know that in Cartesian coordinates, the unit circle is going to look like x squared plus y squared is equal to 1. And when we write it like this, it looks pretty nice. But now if I said solve that expression for y, then we get y is equal to plus or minus the square root of 1 minus x squared. And now it starts looking kind of nasty. And the integration can be kind of gross if we're going to have square roots. So it's much easier to give our region in terms of polar coordinates as opposed to Cartesian coordinates. So we say that the region is the region such that r is between 0 and 1, and theta is between 0 and 2 pi. So that's kind of a nicer way to describe the unit circle here. And then the volume of the solid is going to be the double integral of f of xy over the region R, but we want to write that in terms of polar coordinates now because we're describing our region in terms of polar coordinates. So we have the iterated integral where we have the integral from 0 to 2 pi of the integral from 0 to 1 of 9 minus r squared times r dr d theta. So what happened there with that substitution 9 minus r squared? Well, remember that z is equal to 9 minus x squared minus y squared. We could also write that as z is equal to 9 minus the quantity x squared plus y squared. And we know that x squared plus y squared is equal to r squared. So that's where the 9 minus r squared is coming from. And then we can distribute the r through there. So that gives us a 9r minus r cubed here. And now we're going to evaluate the inner integral. So we have the integral from 0 to 2 pi of 9 halves r squared minus 1/4 r to the 4th, evaluated from 0 to 1. We plug in the 1 and we get a 9 halves minus 1/4. That'll equal 17/4. And so now we have the integral from 0 to 2 pi of 17 over 4 d theta. And that'll give us 17 over 4 theta evaluated from 0 to 2 pi. We plug in our 2 pi and we get 17 halves pi. So that would be the volume of this solid that's bounded above by that paraboloid and below by the unit circle. And finally, we have one last example, and it's probably the most involved example of all of the ones we've done so far. So let's say that we want to find the area of the region R in the plane that's enclosed by x squared plus y squared is equal to 4, above the line y equals 1, and below the line y equals the square root of 3 times x. So again, first order of business is to sketch this region that we're talking about here. So we have our circle of radius 2 in green, we have the line y equals 1 in red, then we have the line y equals the square root of 3 times x in purple, and the region we're talking about is enclosed by these three. So it's that region in blue. So we're going to use polar coordinates in this case to find the area of that region. So the circle x squared plus y squared is equal to 4 is given as the function r equals 2 in polar coordinates. We also want to write both of our lines, y equals the square root of 3 times x and y equals 1 in polar coordinates as well. And remember that for a line that goes through the origin, the equation in polar coordinates is going to be theta is equal to the angle that line makes between itself and the x-axis. So it would be this theta right here for y equals the square root of 3 times x, for example. Okay, so the slope of y equals the square root of 3 times x is the square root of 3. And the square root of 3 divided by 1 is equal to the tangent of theta, where theta is this angle here between our line and the x-axis. And that means that theta has to equal pi over 3, since the inverse tangent of the square root of 3 is equal to pi over 3. So that the line y equals the square root of 3 times x is given by theta is equal to pi over 3 in polar coordinates. We also want to find the point of intersection of our line y equals 1 and our circle r equals 2 now. So we find the intersection of y equals 1 and x squared plus y squared is equal to 4 just by substituting y equals 1 into x squared plus y squared is equal to 4. And we get x squared plus 1 is equal to 4. We do a little bit of algebra, and we find out that x has to be equal to the square root of 3. So the point of intersection of our line y equals 1 and the circle is going to be the square root of 3 as the x-coordinate and 1 as the y-coordinate. So that's the point given in Cartesian coordinates there. We also note that the ray from the origin to the square root of 3, 1. So let me draw that ray up here as well. How about this ray like this? So it's going from the origin to the point given by the square root of 3, 1, makes an angle theta with the x-axis again, so now we're trying to take this ray and write it in terms of polar coordinates. And 1, which is the y coordinate, divided by the x coordinate, which is the square root of 3, is going to equal tangent theta. So that's just some trigonometry there. Again, you can pause the video and think about that for a second if you want to make sure. But it's, anyways, 1 divided by the square root of 3 is equal to tangent of theta, which means that theta has to equal pi over 6. And the importance here is that we're finding our bounds for theta. So we just found that that ray in yellow is theta equals pi over 6, and that ray in purple is going to be theta equals pi over 3. So theta inside of our region, we now know, is going to be between pi over 6 and pi over 3, which is why we found that point of intersection in the first place, because we wanted to find the lower bound for theta. Okay, so now we're getting pretty close. So we know that the area of our region is going to be the following iterated integrals. We have the integral from pi over 6 to pi over 3, those are our bounds for theta, of the integral from something, which we don't know yet, to 2 of r dr d theta. So we have our upper bound for r, because that's just going to be the circle, which has radius 2. But we need to figure out what the lower bound is going to be for r. So if we go down to this other diagram that I have here, again, a nice way to think about what the upper bound for r and the lower bound for r is going to be is by taking rays starting at the origin and drawing them out through the region, and see along what curve the ray is entering the region and on what curve is the ray leaving the region. So here we see that each of these yellow rays that I've drawn, they're always entering on the line y equals 1, and they're exiting on the circle r equals 2. So that's why the upper bound is going to be 2, like I've drawn up here. And the lower bound is going to be the line y equals 1. But now we need to give that line y equals 1 in terms of polar coordinates. Well, we know that y is going to equal r times sine theta, so we substitute that, and we get r times sine theta is equal to 1. And then again, doing a little bit of algebra, we find that r is equal to cosecant of theta. So we divided sine of theta from both sides there. And so now we can fill in for that question mark. So the area of this region is the integral from pi over 6 to pi over 3 of the integral from cosecant theta to 2 of r dr d theta. And now we can just evaluate this double integral. So we start with the inner integral, and we get the antiderivative is 1/2 r squared. And again, we're evaluating from cosine theta to 2. So we plug in a 2, and we get 2 here. And if we plug in cosecant of theta, we get a 1/2 times cosecant squared of theta. And now we're going to evaluate this single integral. So the integral from pi over 6 to pi over 3 of this expression here. Well, this is somewhat of a throwback to Calc 1 or Calc 2, I would suppose. But remember that the derivative of cotangent is equal to negative cosecant squared. And that fact is kind of important for evaluating this integral here. So the antiderivative of 2 is going to be a 2 theta, and the antiderivative of negative 1/2 cosecant squared theta is going to be a positive 1/2 cotangent theta. And again, we're evaluating this from pi over 6 to pi over 3. So we plug both of those values in and subtract when it's appropriate, of course. And again, simplifying, making it look nicer, we end up finding that this is equal to pi minus the square root of 3 all over 3. Okay, so that's how we found the area of this region that was given to us using polar coordinates. I didn't check what the process would be like if we didn't use polar coordinates, but I'm assuming it would be significantly more difficult. So hopefully this shows the power of polar coordinates, the benefits of using polar coordinates at times. And again, the homework for 15.4 will be up shortly, and you can get started on it. And I'll be putting out 15.5 sometime Thursday night, I believe.